So let's go over chapter number 5 of DSP, and in this chapter we are going to look at Z-transforms. Z-transforms are complex frequency transforms. We look at the DSP systems and signal from time domain to complex frequency domain. Z is a complex number, which is sigma plus j omega. If you remember Laplace transform from some other classes, Laplace transform is a complex transform in which you study basically the transient as well as steady state characteristics of systems and signals on which you apply Laplace transform. Z-transform actually is derived from Laplace transform. Laplace transform is for analog signals, and Z-transform is the Laplace transform of discrete signals. In DSP, Z-transform is of utmost importance. You design systems using Z-transforms, your filters basically. And when we say designing filters or designing system, basically we are designing the impulse response of the systems in Z-transform, that is H of Z. H of Z or H of N in time domain, if you remember when we were discussing convolution, we said that if you know the impulse response of a system, you can find the output of the system for any input by taking the convolution. And in Z domain, as you will see, the convolution operation becomes a product. It becomes quite simple to apply convolution in Z-transform when you have the Z-transform of the signals of impulse response signal and the input signal. Then the convolution operation between impulse response signal and the input signal basically becomes a product of those two signals. And then we apply inverse Z-transform to find the time domain response Ys of N once we have Ys of Z from the product of H of Z and X of Z. So Z-transform, as I said, it's a complex frequency transform of digital signal. This is the mathematical expression to calculate Z-transform. So it is an infinite series of the input signal samples times Z to the power negative n. Now Z again is a complex number. We will see in the next chapter that your Z plane, this is the Z plane. Z plane is a complex plane like Laplace plane. On x-axis you have real numbers, negative real number, and on y-axis you have imaginary number, and on the negative y-axis negative imaginary number. So Z can be any complex number. For example, over here it can be 1 plus j2. So Z is a complex number in general. Of course, if Z is on the real axis, then it's going to be a real number, but in general it's a complex number. So we are not going to be using this formula to derive the Z-transform of different signals. Rather, we will be using the Z-transform table, which makes life very easy. So this is a table from your book, and in this table there are 15 relationships between the x of n or y of n, whatever you want to call it, basically time domain signal, discrete signal, and their corresponding Z-transform. So this is x of n is greater or equal to 0, and this is the Z-transform of x of n, which is x of z. Now the important signals, I have highlighted them. Impulse signal, of course, we use very commonly. The Z-transform of impulse signal is 1. Unit step signal we use very commonly. Unit step signal Z-transform is Z over Z minus 1, and if any number is multiplied by unit step signal, then of course you're going to multiply the same number by the unit step Z-transform. NUN, Z over Z minus 1 square. So we use these that are highlighted very commonly, especially we use this one very commonly, we use this one, we do use this one. You will see some of the problems where you have n u n or where you have basically in the Z transform Z over Z minus 1 square. So the inverse Z transform, when we take using again this table, we will write anytime we have this Z transform, we will write in the time domain is going to be NUN. So this table we will be using both for the Z transform as well as inverse Z transform. What is inverse Z transform? Basically, if you have the Z transform, all these things, then inverse Z transform, basically you look at in the table and you see what is the corresponding time domain signal, and basically you just write down that time domain signal from the Z transform, and that's called inverse Z transform. Again, we will not be deriving any inverse Z transform or any Z transform, just this table. So this table is extremely important. Let's see, and one of the most important transform is this one. This is used very commonly, and this is if you have complex conjugate roots of your partial fraction decomposition, as we will study shortly. Okay, so there are three main properties of Z transform that we will be using. The first property is linearity and superposition. That is, if your signal is a1 x1n plus a2 x2n, and you take Z transform of that signal, it will simply become a1 Z transform of x1n plus a2 Z transform of x2n, and Z transform of x1n is x1z, Z transform of x2n is x2z. So a1 x1z plus a2 x2z. Time shift property: if you have a signal x of n, and if you shift that signal by n naught steps, then the Z transform of that will simply be the Z transform of original signal, that is x of n, Z transform of x of n, times z to the power negative n naught. And this is valid if your initial conditions are 0. That is, your voice of if when we do the output using Z transform of x and Z transform of h, so basically your voice of -1, voice of -2, x of -1, x of -2, if those signals are 0, then basically you can write the Z transform of time shift by this, and if you have a plus sign, of course, then it's going to be a plus sign over there. And the last property is convolution, and I just explained it to you, that convolution between two signals, and I'm just using xn and hn because we use these two signals in the previous chapters. So the convolution between two signals in Z domain, it becomes multiplication between the Z transform of those two signals, so xz times h of z, and this generally makes life very easy to calculate y sub z. So you calculate y sub z, and then as you will see from y sub z, which will be a fraction, a fractional form of z, a polynomial in terms of z in the numerator and polynomial in terms of z in the denominator. So from that fraction we create partial fraction in terms of z, and from those partial fraction we use the table and see what is the inverse Z transform, that is what is the corresponding time domain signal, and then we write that for y sub n. That is, we take the inverse Z transform and we write that y sub n is going to be the inverse Z transform of this signal, and we will see shortly how we will solve those problems. Okay, I just see a mistake. This is equal. Calculate y sub z equal x sub z h of z. Alright, example 5.1, we have to determine the Z transform of xn, n plus 20 use of n. So basically we will divide the signal into n plus 20 un, and nun is z over z minus 1 square, z over z minus 1 square, and 20 un is 20 z over z minus 1. That's the Z transform of that, and then I went ahead and I simplified it and gave you the simplified answer. 5.2, determine y sub z if the time domain signal x of n, discrete signal, is 2un, 3un minus 3, and the impulse impulse response is 5un minus 5un minus 2. So how are you going to find y sub z? You have x of n, h of n. First we convert x of n into x of z, and h of n into h of z. And which property we are going to use? We are going to use time shift property on this and time shift property on this, which we are using right over here. 3 un minus 3, 3 times z transform of use of n times z to the power negative 3. So z transform of use of n is z over z minus 1, and then z to the power negative 3. So we are using time shift property, and likewise we are using time shift property on h of z over here. 5 u of n minus 2, 5 times z transform of u of n times z to the power negative 2, and z transform of u of n is z over z minus 1. This is you will be using this very frequently, pretty much in every problem, z transform of step signal. So make sure you remember it's z over z minus 1. And I went ahead, and since we have to calculate y of z, and we know that y of n is the convolution between x of n and h of n, so y of z is the product of x of z and h of z. And we went ahead and multiplied these two together and simplified it a little bit to give you this answer. And we're going to discuss inverse Z transform in the next video.